All right. Okay, let's share my screen so I don't forget this time. So we have to, this class has to be really good because this has to be the one that goes online because I spent the other class, I had a part in the middle where I just made fun of art majors and business majors. And like, I don't want to get canceled, so I can't put that up. I was just like, yeah, I was like, this class has to be good. Like, this can't go up. So what do I get for the first one? Come on, you only know like 3 alkyne reactions, and here are 4. You know 4 alkyne reactions. Here's literally half of them. You do. So you make the vinyl halide, or in this case, vinyl chloride, right? And the halogen goes on the most substituted carbon of the double bond. You only have one equivalent of HCl, so you only have enough HCl to react with one of the 2 pi bonds. So you have to have your pi bond, you have to have a pi bond in the product. What do I get for the other one? See, in the videos, I cut out all the dead space. So it makes it sound like you guys knew the answer right away. Makes you look better. Water sulfuric acid. What atom do you add? Can you just tell me what atom I'm adding to it? Then we can go from there. I'm adding an oxygen, right? So I make an enol. That enol becomes a carbonyl, becomes a C double bond O. So I'm going to make a ketone. I think I have enough carbons. Yes, I have enough carbons. Well, I saw you counting them. Okay, okay, okay. Ooh. Now, what about? So what about those? So what am I going to get for the first one? Yep. So I'm going to make a geminal dihalide or geminal dibromide. So I'm going to put the 2 bromines on the same carbon. I swear that those are actually bonded to that carbon. There you go. Okay. So you got to put 2 bromines on the same carbon. Right, I have 2 equivalents of HBr. So I have enough HBr to react with both pi bonds. So I'm not going to have a pi bond in my product, right, because I reacted with both of them. So I'm going to add both bromines. And then this last one, so I'm going to make a ketone again, right? But it goes on the inside carbon, the more substituted carbon of the triple bond. So there you go. That's everything you know about alkynes so far in 7 minutes. Not bad. Okay. Next up, we're going to do halogenation. This is another reaction like hydrohalogenation, where the number of equivalents that you use matter and change the product. So if you have your alkyne and you use one equivalent of halide, I only have enough halide to react with one pi bond. So I'm going to make a vinyl dihalide, right? And just like halogenation of alkenes, our halide here is going to be Cl2 or Br2. Right, so one equivalent, you end up with a vinyl dihalide. If you have two equivalents, again, you have enough halide to react with both pi bonds. So you're going to end up making a tetrahalide. All right, so you're going to add two halides to the first pi bond, then two halides to the second pi bond, for 4 halides total. Now you're going to add the exact same thing to either side of your alkyne. So what's nice now is it doesn't matter if my internal alkyne is symmetrical or not, because the things I'm adding are symmetrical, right? So if I have an alkyne that's not symmetrical, I still only make one product because I'm adding the exact same group to either side. Someone asked in the early class if we have to worry about stereochemistry, right? Halogenation is an anti-addition. We don't have to worry about wedges and dashes on the two equivalents of Cl2 or Br2 because we don't make a chiral carbon, right? Both carbons that I end up generating have two chlorines on them, so they're not chiral, so wedges and dashes don't matter. So let's do a simple one here for the mechanism. This is really similar to the halogenation mechanism of alkenes, right? So you're going to have your alkyne. It's going to, pi bond is going to add to your chlorine, and just like before, you're going to break your chlorine-chlorine bond. You're going to have your lone pair on your chlorine that you're adding to add back to one of the two carbons of your alkyne. It doesn't matter here. All right. So I know some people have problems on the homework drawing the mechanisms. You just have to make sure that your arrows go to the carbon. I had someone send me their picture, their like screenshots, and they had their arrows went to the bonds as opposed to going to the atoms. So you just have to make sure when you draw your arrow that like the carbon that you're or the atom you're trying to add to, like kind of like gets highlighted blue, so it knows that it's going to there. But now you're gonna get your chloronium ion in this case. And then we can add our chlorine to one of the sides. Push electrons up. Right. So this is our first equivalent, right? Our first Cl2 reacts with the alkyne and we get to an alkene. Now we're just back to the exact same mechanism we had for alkenes, right? So I'm going to redraw this on the next page so I'm not like scrunched at the bottom. So now I'm going to add to my chlorine again, break that bond, have my electrons add back to a carbon. Have your Cl minus. Again, the two sides are the same. So I'm going to add to the carbon, break that bond. So this is basically doing that halogenation of an alkene mechanism. We're effectively just doing it twice. But we're not having to worry about the stereochemical outcome because I don't make any chiral centers in the end. So far, so good. Not too bad. All right. We're good. Okay, now everyone's favorite thing, hydroboration. All right, so here, same reaction conditions that we used for alkenes, but we can generate two different products depending on what our starting material is. So for terminal alkynes, let's start with this. You're going to make aldehydes. So you have your terminal alkyne. Hydroboration is BH3, peroxide, water, and hydroxide. Even with an alkyne, hydroboration still is anti-Markovnikov, meaning that the hydrogen wants to go on the carbon with the most carbons, and the boron / oxygen are going to end up on the carbon with the least number of carbons on it. So you're going to end up making an aldehyde, right? I have enough, I'm only able to react with one of the pi bonds. So the other pi bond from the alkyne ends up being the carbon-carbon double bond. So when I have terminal alkynes, you make a ketone. Internal alkynes, so this is just a more complicated way to make a ketone than what we had before. right? It still has the same kind of problems as using water and sulfuric acid, right? That you need to have a symmetrical alkyne to only make one product. Right? If you have an alkyne that's not symmetrical, you're going to end up making two different products. So you have this. Right, I have two different carbons. Right, there's nothing to differentiate those two carbons. Right, they're both a carbon that's triple bonded to another carbon and then singly bonded to a carbon. So there's nothing to say that one's more substituted than the other. So you just end up with half the time your boron's going to add to the blue carbon and you're going to make this ketone. And the other half the time it's going to add to the green carbon and you're going to make that ketone. So it still has that same problem where we have to have a asymmetrical alkyne to only get one product. So we don't solve any problems. Just if you want to do something that's basic as opposed to something that's acidic, you can use this to make your ketone. So the mechanism is basically the exact same mechanism we had for, make it even simpler, not too far, that we had for alkenes. Right, but I'll walk through it again with you, just to make sure we're all on the same page. Why do I keep adding an extra carbon to this? I just hate myself. There we go. There we go. I even redrew it so it didn't have 4 carbons, and then I messed it up. Again, this is the one that has to go online. So, like, I'm going to edit around that. It'll be fine. It'll be fine. Right, so the first step, shorter arrow. The first step, right, is your boron reacting with your alkyne. So I took my BH3, I kind of drew the one hydrogen out. If you remember, boron is the oddball from the periodic table, right? Everything in the first few like rows has an octet, has 8 electrons around it. Boron only has 6. So boron always has an empty orbital that you can put electrons in. So your alkyne, the pi bond electrons will attack the boron and fill that empty orbital. And then the electrons from the boron hydrogen bond will come down and, it's an arrow, make a bond with your carbon. So that gets you to BH2 and a hydrogen. Now, you're going to keep repeating this process where you're going to have your alkyne add to your boron and the hydrogen on your boron add to your carbon until you run out of boron hydrogen bonds. So I've got 2 boron hydrogen bonds. So that means this can react with 2 more alkynes in pretty much the exact same way it did in the first step. And so I'm going to end up with doing it on there. There we go. That where I have 3 carbons on my boron. I've removed all the boron hydrogen bonds and I've replaced them with boron carbon bonds. So that's the end of the first step over the arrow, right? So the BH3 step, you get to here, you have no more boron hydrogen bonds, done with step 1. So now we use this compound in step 2. We've made that, now we have to use it in step 2. So we take our compound with our 3 carbon boron bonds. We have hydrogen peroxide, and it reacts with hydroxide. Okay, we're gonna erase this and just move it down like 1/4 of an inch so I can actually write. That was frustrating. There we go. And that makes peroxyanion and water. Whew, sorry about that. So now our peroxyanion can add to the empty orbital in boron. Because again, boron has that empty orbital, we can stuff electrons into it. And that gets us to this, where boron has a negative charge, right? The oxygen gave the boron electrons, the boron gets a negative charge. Now, boron doesn't want to have a negative charge, but boron doesn't want to give up its bond to oxygen because boron-oxygen bonds are strong. So as opposed to giving up the boron-oxygen bond, boron's going to give up its carbon bond. So what's going to happen is these electrons are going to push over to the oxygen and push and break the oxygen-oxygen bond because oxygen-oxygen bonds are weak. So that's going to get us to B bonded to carbon, and then O, plus we're going to make hydroxide. Now I think my video is going to have a 33 seconds blinking at me the whole time. Awesome. Just can't win. All right. Now, I want to get rid of the rest of the carbon boron bonds and make them into boron oxygen bonds. So I'm going to use 2 more peroxyanions, and I'm just going to do the exact same step that you just saw. I'm going to do it 2 more times. So I'm going to end up with 3 boron oxygen bonds. So what that ends up looking like is that I've replaced all my carbon boron bonds with boron oxygen bonds. Now, I need to get my oxygens off of my boron, right? I've got the carbon oxygen bond that I want for my product, but I need to get my oxygens off my boron. The way I do that is I have hydroxide in solution, right? I started the reaction with hydroxide, and I was generating hydroxide each time I broke a carbon boron bond. So this reaction's got a lot of hydroxide in it. And that hydroxide is able to add to the boron and push out one of the other oxygens, right? So I just have way more hydroxide than I do boron with oxygens on it. So Le Chatelier's principle takes over, and we push all of the oxygens off our boron. So we end up getting B. We will take 1 off. So we get BOH plus this. Okay. Now, again, I'm going to do this 2 more times to knock off the other boron-oxygen bonds. So I'm going to have more hydroxide come in. And so I'm going to end up making boric acid. Plus 2 more alkoxides. So I've got all, excuse me? Sure, I was going to do it anyway. So I've got 2 here, I've got 2 alkoxides here, plus the one I generated here. So that's all 3 of the groups that were on the boron in the top left are now off of it. The 1 here and then the 2 on the other slide. Sure, thank you. Okay. So now I can use the boric acid or another source of acid, we'll just use the boric acid, to protonate one of these. Let me draw this out a little differently. Right, I'm going to grab a proton off boric acid. And then I'm going to end up with this plus P. So what kind of molecule is in my little orange bracket here? What kind of molecule is that? It's got a double bond, it's got an alcohol. It's an enol. So whenever you see an enol, you know that your enol is going to become a ketone or an aldehyde, right? So I've got my enol. That's going to tautomerize to be your aldehyde. Right, so you know as soon as you make your enol that it's going to become a C double bond O.
I got to ask to show where all 3 oxygens were that were on the boron initially.
So there's 3. If you go 1, 2, 3. All 3 are accounted for, right? I do it once and I take off the first one. And then I assume, like in all these things where I'm like, you do it 2 more times, I assume if you could draw the arrows correctly the first time, that you can draw the arrows correctly for the next 2. So then I just kind of roll it out or roll it up into one where you make the boric acid and then you generate 2 more of that alkoxide, as opposed to having you draw the same step basically over and over and over again. But yeah, all 3 are accounted for. Sure. So basically the same mechanism we did with the alkene. The only difference is once you get to the alcohol, you have the one extra step of turning that enol into carbonyl. But that's it. Again, I can't really dress these up at all, right? Like it's just always going to be, oh, terminal alkyne and BH3. You're gonna make an aldehyde, right? There's nothing tricky I can do with it. It's just everything comes along for the ride. You're reacting with the alkyne, making an aldehyde. Oops, what am I doing? Drugs are bad, boys and girls. Internal alkyne, just make a ketone. Nothing real tricky. See, as long as I got down too far, I can just trim the 33 seconds off the video and you'll never know it's there. Yes, I've got to like make sure I just stay above it. Then I can crop it. Yeah. Because I always crop out the little tools at the top so you can't see those in the video. And we make these high quality. That's right. Someone went to the school of YouTube editing. That's right. YouTube, how do I do this? Oh, excellent. Boop. Okay. So the last thing I want to talk about is hydrogenation. All right. And so with this, you can remove all or some. I will do it this way. Some or all of the, oh, I should have done it another way, of the pi bonds of your alkyne. So you can go from alkyne to alkene with one set of reagents, or you can go alkyne all the way to alkane with another set of reagents. The easiest is when you just take all the pi bonds away. So we're going to start with this. We're talking about going from alkynes to alkanes. So this is basically using the same reaction that we used for turning an alkene into an alkane. So just like H2, palladium on carbon, is going to remove all of your pi bonds, and you're just going to end up making an alkane. You can also do this with platinum on carbon, does the same thing. And you're good, right? There's like nothing to this other than to see H2 palladium on carbon or H2 platinum on carbon, alkyne goes away. I think the hardest part is just making sure you count and you have the right number of carbons in your starting material versus in your product, because a lot of people will like lose track of their carbons. So, right, you just have to be like, okay, an alkyne here is 2 carbons, so I need to make sure that I have 2 carbons between the 2 groups. So you're like, oh, 6-membered ring, 2 carbons, isopropyl group, right? So you just have 1, 2, 1, 2. We don't have to worry about stereochemistry because just like when we did the halogenations, right? I'm adding 4 hydrogens. So when I add 4 hydrogens, I don't make any chiral centers. So it doesn't matter which hydrogen is on a wedge and which one's on a dash, because the blue carbon and the green carbon are not chiral. So it's just basically erase your 2 pi bonds and you're done. Right? Now, when we only go from alkyne to alkene, here we have to worry about double bond stereochemistry. So we have to worry about if we're going to make the cis double bond or the trans double bond. And depending on what reagents we use, we can choose. So the first thing is going to be Lindlar's catalyst. So this is palladium on barium sulfate and quinoline. So it's palladium absorbed or adsorbed onto a different solid. So instead of being on carbon, it's on barium sulfate. And you have quinoline. And quinoline has a nitrogen on it. And so that nitrogen binds to the palladium and poisons the palladium catalyst. Basically makes it so the palladium is not as reactive as it would be if the quinoline wasn't there. And what that means is Lindlar's catalyst is only able to reduce an alkyne once. It goes from alkyne to cis alkene. For the most part, I think every time I've ever put this on an exam, it's just Lindlar's catalyst. Like 99% of the time, you're just going to see it written as Lindlar's catalyst. But if you see palladium on barium sulfate with quinoline, that's what Lindlar's catalyst is. That's what that name is wrapping up the reagents. So you have your alkyne, you have your H2, and you have Lindlar's catalyst, and you make a cis double bond. Right? This kind of makes sense if you think about how this works kind of physically. Right? We're not going to go through the mechanism, but like the kindergartner mechanism, right, is palladium rips H2 in half and holds like a poor defenseless little hydrogen in each palladium arm, right? And then just sticks those two hydrogens on the alkyne from the same side, right? So those two hydrogens end up on the same side of the double bond, which means the two groups that were originally on the alkyne, they have to end up on the same side, right? They get pushed in the same direction because the palladium just comes up and goes, yeah, and sticks them on the. So the hard part now is I have to figure out, do I go home and film myself going, ah, and cut that into the video or not? Like that is the thing that I have to figure out how to do for the people, right? They're like, why did he make that noise? And they have to just see me go, yeah, and I have to do it like 3 times, right? But it just sticks the hydrogens on the same side. So again, it doesn't matter what alkyne you start with, what's going on, right? You're always just gonna make the cis double bond. So you just wherever your alkyne is, cis double bond, and you are good. Yeah, like when I did like when I brought the models in, I actually sat in front of my computer and redid the models and try to time it up with the explanation. It's so hard because I couldn't hear it. It's just like I hadn't figured that out on YouTube yet. I was like, I'll just guess. It's fine. And when I'm really far off, I just slow myself down so the video's slower. It lines up. Yeah, this is what your tuition dollars is going to, is that kind of high quality production. Yeah, my lip syncing's off. I'll just slow it down. It'll be fine. All right. Now, if you want to make a trans double bond, there's another set of reactions or reagents to use. So here, you take sodium metal. So I have this little 0 here. And that 0 is just indicating that it's the actual metal. It's in the 0 oxidation state. So it is just legitimately sodium metal. And you put it in ammonia. And that will always make the trans double bond. You can do this with sodium, or you can do it with lithium. And you're always going to get the trans double bond. And again, lithium in the 0 oxidation state. It doesn't have to have the 0. It's just understood that it's just going to be lithium or sodium metal. It can also be written, you also may see it written like like lithium slash NH3. So when you run this reaction like in a lab, you actually will take your ammonia gas and you'll condense it into a liquid. So you like blow it over dry ice, which condenses it into a liquid. And then as you put your metal in, your metal will kind of instantaneously dissolve as it goes in and it becomes ions in solution. So these are sometimes called dissolving metal reductions because the metal quite literally dissolves in the ammonia as you add it. Now this is exactly where I got in the early class. So we'll do the mechanism on Monday.